Hello, testing, testing. Hello. Hi, Marisa. Your mic's not broken. Hello, hello. I turned my mic to a... PogChamp Senpai says hello. Hello. Let me turn the music off. Hello, hi everyone. Good evening. It's bedtime. It's time for me to read you a bedtime story to help you fall asleep. Which bedtime story? Oh, what about System Design Interview? An Insider's Guide by Alex Shu. Wow, just like what my father used to read to me to put me to sleep. I have no idea what's going to happen in this stream. I tested my mic settings so that I can put it to the max sensitivity. I did a quick test before the stream. I have no idea if it's going to work or if it's going to sound absolute garbage. I'm just going to hope for the best. Hopefully the sound is good. Okay, are you guys ready for the bedtime story? Sorry. Okay, we're going to be reading System Design Interview, An Insider's Guide by Alex Shu. Are you guys ready? Is there a way I can hide the table of contents on the side here? Oh, there we go. Ooh. Cool, now it looks way cleaner. I also want to scoot it to the side a little bit so you can see the moon. There we go, that's pretty nice. Okay, are you guys ready? So, in case you guys don't know what system design is, it's basically when you have a bunch of computer servers or computer nodes and you're asked, okay, this is the app description. How are you going to build this app, assuming that it's distributed across multiple servers? For example, what are your different servers going to do? Is one of them going to be a database? Is one of them going to be a cache? Is one going to be a front end, another back end, that kind of deal? That's what system design is. It's kind of given an app description. How do you structure and lay out all of your servers? What types of servers are you going to use in combination with each other to get the app working? Okay, let's start with chapter 1. Chapter 1. Scale from 0 to millions of users. Designing a system that supports millions of users is challenging, and it is a journey that requires continuous refinement and endless improvement. In this chapter, we build a system that supports a single user and gradually scale it up to serve millions of users. After reading this chapter, you will master a handful of techniques that will help you to crack the system design interview questions. Oh yeah, and system design is often asked during coding interviews, so it's useful to study. Single server setup. A journey of 1,000 miles begins with a single step, and building a complex system is no different. To start with something simple, everything is running on a single server. Figure 1-1 shows the illustration of a single server setup where everything is running on one server: web app, database, cache, etc. Okay, so I guess this is the most basic system design ever. Everything running on one server. One server handles web browser traffic, mobile apps, your DNS lookups. Wait, no, I got that wrong. I'm so sorry. So the user is calling from a web browser and a mobile app, and the app is hosted 100% on one web server. Very simple app. And their internet provider takes care of the DNS lookup for the IP addresses or URLs. To understand this step, it is helpful to investigate the request flow and traffic source. Let us first look at the request flow. So again, this is everything, the entire app hosted on one server. The most simplest system design that you can do. Okay, number 1. Users access websites through domain names such as api.mysite.com. Usually, the domain name system, DNS, is a paid service provided by third parties and not hosted by our servers. Internet Protocol, IP address, is returned to the browser or mobile app. In the example, IP address 15.125.23.214 is returned. So let's say the user is on the web browser over here. They shoot a DNS request to a third party, maybe it's an internet provider, and they're like, what's the IP address to the app that I'm trying to look up? DNS service is like, here it is, and gives it back to the user in the web browser. To be honest, I don't really understand how DNS works. Once the IP address is obtained, Hypertext Transfer Protocol, HTTP, requests are sent directly to your web server. The web server returns HTML pages or JSON response for rendering. Next, let us examine the traffic source. The traffic to your web server comes from two sources: web application and mobile application. Web application. It uses a combination of server-side languages, Java, Python, etc., to handle business logic, storage, etc., and client-side languages, HTML and JavaScript, for presentation. Mobile application, HTTP protocol, is the common protocol between the mobile app and the web server. JavaScript Object Notation JSON is commonly used API response format to transfer data due to its simplicity. An example of the API response in JSON format is shown below. Alright, this is just JSON. Arpit says LeetCode. No, no leak code today. I'm reading System Design as sort of a ASMR parody. I haven't read this book in so long. Database. With the growth of the user base, one server is not enough, and we need multiple servers. One for web/mobile traffic, the other for the database. Separating web/mobile traffic, web tier, and database data tier servers allows them to be scaled independently. Oh yeah, the company where I work at actually did something similar to this, like hosting the entire, well, they didn't host the entire service on one app server. What they did was, for certain data, they would actually store it as CSV files locally on the web server. And that worked until it didn't. Like, there's only so much you can store on CSV files locally. And then later, when the storage got too resource intensive, they actually did move to real databases. So this is kind of relatable to a certain extent. Arpit says, will you stream the next weekly contest? Yeah, I will. It's the one at 7:30 p.m., right? Yeah, I will. Don't worry. Okay, so basically a database is a server that stores like data. Which databases to use? You can choose between a traditional relational database and a non-relational database. Let us examine their differences. Relational databases are also called a Relational Database Management System, RDBMS, or SQL database. The most popular ones are MySQL, Oracle database, Postgres, SQL, etc. Relational databases represent and store data in tables and rows. You can perform join operations using SQL across different database tables. Non-relational databases are also called NoSQL databases. Popular ones are CouchDB, Neo4j, Cassandra, HBase, Amazon DynamoDB, etc. These databases are grouped into 4 categories: key-value stores, graph stores, column stores, and document stores. Join operations are generally not supported in non-relational databases. The only one I recognize here is DynamoDB. I'm so screwed. For most developers, relational databases are the best option because they have been around for over 40 years. And historically, they have worked well. However, if relational databases are not suitable for your specific use cases, it is critical to explore beyond relational databases. Non-relational databases might be the right choice if your applications requires super low latency. I wonder why non-relational databases give you super low latency. Is it because they're in key value format? Maybe actually. If the non-relational databases are stored in key value format, then access time of any data, it's going to be OM1 time, right? Yeah, because that's how hashes work, right? You just calculate the index that they're at and fetch that index. While I guess in relational databases, you can index the data, right? But that gives you at best log n time. because indices are stored in a tree-like structure, right? Arpit says, are you a full stack developer? Oh, that's a good question. Am I? I think I kind of am right now. I actually entered my company as a back-end engineer, but through the power of vibe coding, I use cursor a lot at work. Through the power of vibe coding, I now work in front-end as well. I now work in both front-end and back-end, and I have helped set up like BigQuery databases. You know what? Yeah, I totally am a full stack right now. I think this is due to the help of vibe coding. Anyways, your data are unstructured, or you do not have any relational data. Relational being tabular data, I guess. I guess that makes sense. You only need to serialize and deserialize data, like in JSON, XML, YAML, etc. Yeah, that makes sense. You need to store a massive amount of data. Why would non-relational databases give you an advantage here? Can't you also store, or is it because the larger your relational database is, the higher the latency will be? Yeah, that's probably it. Because, yeah, the non-relational database will always be a one-time, right? Assuming it's key value storage format. And then relational databases are at best log n time, which will get worse the more data you have. I guess that makes sense. Yeah, I guess that makes sense. Arpit says, hey bro, currently I entered the third year of my college. I only did LeetCode and competitive programming now. I have started learning full stack development. Please suggest the best way to practice it. I guess the best way to practice it is to just make stuff. Yeah, think of projects that you want to work on. Like, the best way to learn anything is to learn the absolute minimal basics first, and then just start making things with it. For example, I really wanted to learn game dev when I was in high school. I YouTubed. At the time, Unity had a really basic rollerball tutorial on their homepage or something. So I did that as a beginner tutorial. That tutorial gave me the basics I needed to, I guess, start making games, and gave me just a little bit of knowledge so I know how to look up stuff when I get stuck. And I guess that's how I started learning the game engine Unity. I took the most basic tutorial that they had, and then I just started making games. Anytime I had a question or I didn't know how to do anything, I just Googled it, looked it up, YouTubed it. Honestly, with ChatGPT now and LLMs, it should be really easy to look up stuff for anything that you're learning, actually. Especially if it's like full stack, because yeah, web development, well, it depends on the frameworks that you're using, actually. If you're using like React or, I don't know, Express.js, common frameworks, it should be easy to just ask ChatGPT, how do I do that? How do I do this? What are some best practices you know? Yeah. Vertical scaling versus horizontal scaling. Vertical scaling, referred to as a scale-up, means the process of adding more power, CPU, RAM, etc. to your servers. Horizontal scaling referred to as scale out, allows you to scale by adding more servers into your pool of resources. When traffic is low, vertical scaling is a great option. And the simplicity of vertical scaling is its main advantage. Unfortunately, it comes with serious limitations. Vertical scaling has a hard limit. It is impossible to add unlimited CPU and memory to a single server. I see, makes sense. Vertical scaling does not have failover and redundancy. If one server goes down, the website/app goes down with it completely. Yeah, that's not good. Horizontal scaling is more desirable for large-scale applications due to the limitations of vertical scaling. In the previous design, users are connected to the web servers directly. Users will be unable to access the website if the web server is offline. In another scenario, if many users access the web server simultaneously and it reaches the web server's load limit, users generally experience slower response or fail to connect to the server. A load balancer is the best technique to address these problems. Oh. Right on cue. Load balancer. A load balancer evenly distributes incoming traffic among web servers that are defined in a load balance set. I don't understand what I just read. A load balancer evenly distributes incoming traffic among web servers that are defined in a load balance set. Figure 1-4 shows how a load balancer works. So a user tries to access your app from a web browser or a mobile app. It looks up your location using DNS. Then it goes to a load balancer, which is, I guess, a server that determines which server you should pass your request to, depending on which server is more available or which server is more alive. As shown in figure 1-4, users connect to the public IP of the load balancer directly. With this setup, web servers are unreachable directly by clients anymore. But for good reason, I guess. For better security, private IPs are used for communication between servers. A private IP is an IP address reachable only between servers in the same network. However, it is unreachable over the internet. The load balancer communicates with web servers through private IPs. In figure 1-4, after a load balancer and a second web server are added, we successfully solved no failover issue and improved the availability of the web tier. Details are explained below. If server 1 goes offline, all the traffic will be routed to server 2. This prevents the website from going offline. We will also add a new healthy web server to the server pool to balance the load. Excuse me. If the web server traffic grows rapidly and 2 servers are not enough to handle the traffic, the load balancer can handle this problem gracefully. You only need to add more servers to the web server pool, and the load balancer automatically starts to send requests to them. Now the web tier looks good. What about the data tier? The current design has one database, so it does not support failover and redundancy. Database replication is a common technique to address those problems. Let us take a look. Give me one moment. Database replication. Quoted from Wikipedia. Database replication can be used in many database management systems. usually with a master/slave relationship between the original, master, and the copies, slaves. A master database generally only supports write operations. A slave database gets copies of the data from the master database and only supports read operations. All the data modifying commands like insert, delete, or update must be sent to the master database. Most applications require a much higher ratio of reads to writes. Thus, the number of slave databases in a system is usually larger than the number of master databases. I see, so the slave databases are used for reading. The master database are used for writing. I see. Figure 1-5 shows a master database with multiple slave databases. So these are your web servers. Writes go to the master database. Reads go to the slave database. Database replication happens between the master database and the slave database. Advantages of database replication. Better performance. In the master-slave model, all writes and updates happen in master nodes, whereas read operations are distributed across slave nodes. This model improves performance because it allows more queries to be processed in parallel. Reliability. If one of your database servers is destroyed by a natural disaster, such as a typhoon or an earthquake, data is still preserved. You do not need to worry about data loss because data is replicated across multiple locations. I think one of your slave databases can then be promoted to become the master database. Excuse me while I drink some water. High availability. By replicating data across different locations, your website remains in operation even if a database is offline, as you can access data stored in another database server. In the previous section, we discussed how a load balancer helped to improve a system availability. We asked the same question here. What if one of the databases goes offline? The architectural design discussed in Figure 1-5 can handle this case. If only one slave database is available and it goes offline, read operations will be directed to the master database temporarily. Makes sense. As soon as the issue is found, a new slave database will replace the old one. In case multiple slave databases are available, read operations are redirected to the other healthy slave database. A new database server will replace the old one. If the master database goes offline, a slave database will be promoted to the new master. All the database operations will be temporarily executed on the new master database. Why temporarily executed? Doesn't that slave database just become the master database forever? A new slave database will replace the old one for data replication. Immediately. A new slave database will replace the old one for data replication immediately. Makes sense. In production systems, promoting a new master is more complicated, as the data in slave database might not be up to date. The missing data needs to be updated by running data recovery scripts. Although some other replication methods like multi-masters and circular replication could help, those setups are more complicated, and their discussions are beyond the scope of this book. Interested readers should refer to the listed reference materials. Figure 1-6 shows the system design after adding the load balancer and database replication. Ooh, very exciting. Okay, so you have a user who could be trying to access you from a web browser or a mobile app. They get your IP address or URL from a DNS server. They try, I guess the DNS server will give you the IP address, the public IP address of the load balancer. Then once you reach the load balancer, the load balancer will decide which server to direct you to, depending on which one is available, which one is experiencing the least traffic, stuff like that. And then each individual server will write to the master database and read from the slave databases. Makes sense. Now you have a solid understanding of the web and data tiers. It is time to improve the load/response time. This can be done by adding a cache layer and a shifting static content, JavaScript, CSS, image/video files to the Content Delivery Network, CDN. Okay. I'll probably read the cache part and then I'll go to sleep. Hopefully that's okay with you. So a cache, excuse me one moment. So a cache is a temporary storage area that stores the result of the expensive responses or frequently accessed data in memory so that the subsequent requests are served more quickly. As illustrated in figure 1.6, every time a new web page loads, one or more database calls are executed to fetch data. The application performance is greatly affected by calling the database repeatedly. The cache can mitigate this problem. Cache tier. The cache tier is a temporary data store layer, much faster than the database. The benefits of having a separate cache tier include better system performance, ability to reduce database workloads, and the ability to scale the cache tier independently. Figure 1-7 shows a possible setup of a cache server. So you have a web server here. If data exists in cache, read data from cache. If data does not exist in cache, save data to cache after getting it from the database, I suppose, and then return the data to the web server. Silo says, hello, I'm traveling right now. What design is this? System web? It is system design. Though if you're talking about web design, I think it kind of overlaps too, because we're talking about web servers, caching databases, stuff like that. I think those are related to web design too, right? Maybe system design and web design have overlaps. After receiving a request, a web server first checks if the cache has the available response. If it has, it sends data back to the client. Excuse me. If not, it queries the database, stores the response in cache, and sends it back to the client. This caching strategy is called a read-through cache. Other caching strategies are available depending on the data type, size, and access patterns. A previous study explains how different caching strategies work. 6. Interacting with cache servers is simple because most cache servers provide APIs for common programming languages. The following code snippet shows a typical memcached APIs. Memcached as in memory cached APIs, I suppose, like they're stored in RAM. Seconds equals 1. Cache.set my key the value, comma, the expiration time, I suppose, the time to live, TTL, cache.get my key. Yeah, so this is how you set stuff, key value pairs on the server in cache. And then this is how you get key pairs. I guess just key values from the pairs. Silas says, neat. I learned about operating system last semester, paging, pooling, caching, RAID, and a few more stuff. Hey, that's pretty neat. Yeah, some of that overlaps with what I'm reading right now, like, I don't know, caching. Well, just caching. Maybe the rest of this book will touch on more stuff in the future, though. Here are a few considerations for using a cache system. Decide when to use cache. Consider using cache when data is read frequently, but modified infrequently. Oh yeah, because you have to worry about updating the cache data too, right? Or setting a TTL low enough that, the latency is more tolerable. Since cache data is stored in volatile memory, a cache server is not ideal for persisting data. Yeah, exactly like I thought. For instance, if a cache server restarts, all the data in memory is lost. Thus, important data should be saved in persistent data stores. But yeah, you will be so stupid to store all important data in caches. Like, electricity goes out, whole company is screwed. Expiration policy. It is good practice to implement an expiration policy. Once cache data is expired, it is removed from the cache. When there is no expiration policy, cache data will be stored in the memory permanently. It is advisable not to make the expiration date too short, as this will cause the system to reload data from the database too frequently. Meanwhile, it is advisable not to make the expiration date too long, as the data can become stale. Consistency. This involves keeping the data store and the cache in sync. I'm guessing to do this, you could set your TTL to a really low value. Inconsistency can happen because data modifying operations on the data store and cache are not in a single transaction. When scaling across multiple regions, maintaining consistency between the data store and cache is challenging. For further details, refer to the paper titled Scaling Memcache at Facebook, published by Facebook. Mitigating failures. A single cache server represents a potential single point of failure, SPOF. Defined in Wikipedia as follows. A single point of failure, SPOF, is a part of a system that, if it fails, will stop the entire system from working. As a result, multiple cache servers across different data centers are recommended to avoid SPOF. Another recommended approach is to over-provision the required memory by certain percentages. This provides a buffer as the memory usage increases. So if you have multiple computers and they use all the same router, which is backed by an application server, if you only have one router and that router breaks, you're kind of screwed. Makes sense. Eviction policy. Once the cache is full, any request to add items in the cache might cause existing items to be removed. This is called cache eviction. Least recently used LRU is the most popular cache eviction policy. LRU also happens to be a really hard LeetCode code question. I don't even remember currently how to do it. I think we have to use some sort of hash map. There's like sorted versions of hash maps in Java and Python, right? Other eviction policies, such as the least frequently used, LFU, or first in, first out, FIFO, can be adopted to satisfy different use cases. So, based on the names, least frequently used sounds like you track the counts of how many fetches are there for each key-value pair. And then if you want to evict something, evict the one with the least usage. Maybe you track that with the priority queue or something. First in, first out. First in, first out. The first thing that's ever cached will be evicted once you run out of space. I see. Oh look, we're doing CDNs now. Content Delivery Networks. Oh, it's actually kind of late in my time zone. We've been reading for 46 minutes. Well, hopefully those of you who are listening right now are either fast asleep or completely confused by what you are hearing right now. Hopefully the former. I'm just gonna assume, for optimism's sake, that you are asleep, and I will close this book and quietly tiptoe out of your room. Okay, I think I'm going to end the stream over here. Thanks everyone who are coming. Hopefully you sleep well. Have a good night. Goodbye.